The spectacle unfolding behind me here is a graphic demonstration of buoyant force. Amazingly, the buoyant force acting on a hot air balloon is able to lift a basket filled with passengers. This powerful force appears whenever an object is immersed in a fluid. Do you know what fluid this hot air balloon is immersed in? Remember that both liquids and gases are fluids. The fluid surrounding the balloon is air. Let's investigate the buoyant force in another fluid, water. This is a concrete block. This is a wood block, a softwood block, pine actually. I'm going to drop these two blocks into the water in the aquarium. One will sink, one will float. You probably have a prediction about what's going to happen. Let's find out. I suspect your prediction was correct, that the concrete block sinks. When I ask the question, why does the concrete block sink? The answer often is the concrete block is heavier than the wood block. We have to be careful with our vocabulary and understanding here. Consider a cruise ship. More buoyant force. This cruise ship behind me is in fact a huge hotel floating on the surface of the ocean. These huge ships can weigh over 50,000 tons. Despite this huge weight, cruise ships have no problem floating on the ocean. Whether an object sinks or floats is not determined by its weight, but by its density and the density of the fluid it is immersed in. Density is mass per unit volume. Let's calculate the density of our two blocks and the water they are immersed in. To calculate density, we divide the mass of an object by its volume. Our concrete block is a rectangular prism. You determine the volume of a rectangular prism by multiplying its length times its width times its height. The length of our concrete block is 7 centimeters. Its width is 5 centimeters, and its height is also 5 centimeters. 7 by 5 by 5 centimeters. Doing the multiplication, we find the volume is 175 cubic centimeters. Now we need to determine the mass of the block. Using a digital scale, we find the mass of our concrete block is 400 grams. Density equals mass divided by volume. Doing the division, we find the density of our concrete block is 2.3 grams per cubic centimeter. We will calculate the density of our wood block using the same method. Measure length, width, and height. Then multiply to determine the volume. This wood block has a volume of 388 cubic centimeters. The digital scale tells us this block has a mass of 161 grams. Inserting the numbers into the density formula, we determine that this wood block has a density of 0.4 grams per cubic centimeter. I rounded the results to 1 decimal place. Now to calculate the density of water. Let's determine a volume of water using a graduated cylinder. This graduated cylinder is calibrated in milliliters, the common volume unit for liquids. 1 milliliter is equal to 1 cubic centimeter. Because we will be measuring the mass of the water in the cylinder, we need to subtract the mass of the cylinder from the total mass of the water plus cylinder. A digital scale makes that easy to do. Sit the empty cylinder on the scale. The mass of the cylinder is displayed as 110 grams. Press tare, and the mass of the cylinder is subtracted. I can now remove the cylinder, fill it with water to the 250 milliliter mark, and sit it back on the scale. We have 249 grams of water. Doing the math, we divide mass by volume, and rounding the answer to 1 decimal place, we determine the density of water to be 1 gram per cubic centimeter. That's interesting. 1 cubic centimeter of water has a mass of 1 gram. This is not a coincidence. If you research the history of the metric system, you will find that the first standard metric unit of mass, the gram, was defined as the mass of 1 cubic centimeter of water. Getting back to our investigation of density and buoyant force, this table shows the wood is less dense than water and that the concrete is more dense than water. The wood block floated while the concrete sunk. A conclusion from this data is that objects denser than water will sink in water, while objects less dense than water will float on water. This is true for other fluids, not just water. This means that the cruise ship, even though it is extremely heavy, is less dense than salt water. This is because a large portion of the volume of the cruise ship is air. Sometimes an object neither sinks nor floats. We say it has neutral buoyancy. Fish can adjust their density to maintain a state of neutral buoyancy. They do this by inflating an internal bladder with air. This organ changes the volume of the fish without changing its mass, allowing it to match its density to the water it is swimming in. Scuba divers use a similar method with an external bladder to control their buoyancy. Human beings are very close to having a neutral buoyancy. The makeup of each individual determines whether they sink or float. We have demonstrated that density determines whether an object will sink or float, but we have not explained where the buoyant force comes from. When an object is placed in a fluid, it displaces or pushes out of the way some of the fluid. This displaced fluid pushes back on the object. This is buoyant force. All objects in a fluid experience buoyant force. Even the concrete block on the bottom of the aquarium is experiencing a buoyant force, but the force is not strong enough to lift the block. The Greek philosopher and scientist Archimedes is credited with figuring this out. The science behind buoyant force is known as Archimedes Principle. This principle states, the buoyant force on a submerged object is equal to the weight of the fluid that is displaced by the object. This means that the denser a floating object is, the more water it will displace. An object with a density of 0.5 grams per cubic centimeter will float only partly submerged, while an object with a density of 0.9 grams per cubic centimeter will float almost completely submerged. Another interesting thing about buoyant force is that gravity plays a role. You may know that pressure in water increases as you dive deeper in a lake. Gravity creates this pressure gradient, and it is an essential part of buoyant force. It is not possible to create a buoyant force without gravity. Let's take another look at hot air balloons. We know that in order to float, a hot air balloon, complete with its passengers, must be less dense than air. Air has a density of only 1/1000th of a gram per cubic centimeter. Here is how the balloon attains such a low density. First of all, the balloon is huge. It has an incredible volume, typically 3,000 cubic meters, filled with air. The challenge is to reduce the mass of the air in the balloon. That is where the heat comes in. When air is heated, the air molecules pick up energy, increasing air pressure in the balloon. The balloon has an opening at the bottom. This allows pressurized air to escape, reducing the mass of air in the balloon. When enough air has escaped, the huge volume of the balloon, combined with its reduced mass, lowers the balloon's density below the density of the surrounding air, creating positive buoyancy. The balloon, with its passengers, floats into the atmosphere. That concludes our look at density and buoyant force. I'll leave you with 3 questions. 1. Do ice and water have the same density? 2. How does moving from salt water to fresh water affect a ship? 3. Why does a helium balloon rise in air? Think about density and buoyant force when answering these questions.